Okay, hello everyone. So as the people is joining the room, I think we can start. I'm starting with a brief introduction for today's talk. As you know, I am the chair of this IEEE Signal Processing Society Autonomous System Initiative. And it's my pleasure today to have with us to introduce Dr. Arash Ajoudani. But before introducing him, let me also talk about very briefly about the next webinar we are going to have at the end of April, 27th of April, as you can see from the slide, from Professor Jackie Ma from the University of California, Los Angeles. And he will talk about cooperative perception all at once with OpenCDA. And also let me remind you the initiative we are organizing at the next ICASP that will be in Greece from June 4 to 9 in Rhode Island. I hope I can meet you in person there. Okay, so let me introduce today's webinar. So we have the pleasure to have with us Dr. Arash Ajoudani. So let me briefly introduce him. Arash is the director of Human Robot Interface and Interaction Laboratory at IIT in Genova, Italy. He also coordinates the robotics for manufacturing lab at Leonardo Labs, and is principal investigator of the IIT IntelliMech Joint Lab. He received a PhD degree in robotics and automation from University of Pisa in 2014. And was a joint PhD with the IIT, of course. Okay, so we have approximately 1 hour for the talk, so I kindly invite you to wait for the end for putting question. You can, at the end of the talk, you are free to open your microphone and put questions, or if you prefer to write questions on the chat. Okay, so Arash, the floor is yours.
Thank you very much, Socio, and thanks for the introduction and the invitation. It's a big honor. It's the first time for me to give a talk in the signal processing community. I'm mostly involved in the robotics community, and I hope this brings a lot of mutual collaboration between these two communities. I'll try and share my screen. Hope that everything will be smooth. All right. So I slightly changed the topic of my talk because I think people in this talk are more interested into control and processing aspects, and I'll be focusing mostly on let's say robotics parts and control and signal processing. Just about some projects that I've been working on, especially the ERC grant of mine and the project Horizon 2020 Sophia that is under my coordination, and also coordination of concert project. These are mostly the external fundings, of course, also INEL national fundings that are contributing to this research that I'm presenting. And of course, the work you see are results of so many researchers in the labs that I'm coordinating, and I would like to thank them all. Just to give you an image of a future, let's say, industrial application, it can be production, it can be logistics, or any service industry that you can have in mind. Alternate, of course, in long time in future, maybe you want to have very autonomous robots, but a long horizon in the middle, which will be an intermediate integration. We will have machines and humans working together, and machines will take the repetitive and, let's say, power demanding tasks and responsibilities of the jobs, and humans will be there to transfer knowledge, to teach the robots, to always seek for areas of improvement, to implement the concepts of lean production or lean manufacturing or lean robotics. And therefore, it will be really important to create a synergistic, let's say, interaction in between them. In fact, in all these scenarios that you can see here, you will see the most common element here is interaction between robots and objects, interaction between robots and environment, interaction between humans and objects, between 2 robots, 3 robots of different types, and also interaction between humans and robots of different types. So it's important to understand how we can classify and make sure that the controllers, especially in terms of interaction, are significant and robust enough that we can ensure a good interaction between robots, environment, objects, and humans. So if we put the elements of robot interaction and autonomy to boost these elements of, let's say, 1 by 1 to have robots that are autonomous, but profoundly they are also collaborative between each other and between the humans, we can classify these into the corpus, which is the body of the robot, their interfaces, learning and control techniques that make these systems interact with the environment, and the human, that we can actually divide these human factors to social and physical. So we have a mixed approach towards integrating and developing technologies. Up to some extent, we are working on classical control techniques, and when the benefits of learning and machine learning tools are evident, we integrate machine learning tools. I always like to cite this sentence by the British statistic expert, which says all models are wrong, but some are useful. So it's good to always have a model of the environment or a model of the task or the person, and for the parts that we cannot model or are very time varying and with a lot of uncertainty, we can definitely make use of machine learning approaches. So to start with the creation of synergies between these components, I will just try to tell you how this corpus through learning and control can interact with the environment. So these are some of the examples that we've been developing how robots can interact with the environment. First ingredient will be through, of course, visual perception. So you can perceive the environment through various techniques that we have also implemented in machine learning, that we know that it's really useful to train deep neural networks to be able to distinguish objects, for instance, of various size, and we can have, let's say, different behaviors in a sense that everything is not pre-planned, to be very flexible with respect to the perception and manipulation. So vision, let's call it the first ingredient of improving, let's say, robot interaction autonomy, because you can see and you can perform the action, right? But of course, touch is as important as the vision, especially it contains some information that can be helpful in planning. Most of the time, us humans, when we do manipulation tasks, we rely on touch and haptic information to be able to, for instance, to navigate, to perform a task. Even sometimes when we lose attention towards performing a task, we always use the information of, let's say, that coming from our force or feet or haptic sensory system. So just to give you an idea of how this can work only by relying on touch, imagine you have a robot that wants to go through the maze. This example can be an example of an electrician that comes to your house and it tries to find, to insert a cable from one hole that comes from the other hole without even knowing how the path of the maze looks like. You can insert the path, the rod, and from the other side comes out only by relying on the constraints that come from the environment. So what we are doing there, we are building the robot dynamics system by understanding how we can control the quasi-static behavior of the robot, which comes down to stiffness and damping of the robot, by projecting these components into certain directions and creating the same behavior that, let's say, that wiring rod will replicate. Just to give you an example, for instance, if you have soft constraints, you can process data and always by relying on the force data that you're getting from the interaction with the environment, you can update your path, you can update your equilibrium pose to be always to comply with the constraints, with the soft constraints that you have, without even knowing how the surface looks like. It's like opening a door, right? So basically you have a constraint, physical constraint from the environment, but you always rely and use those constraints to be able to slide on this surface. Obviously, this doesn't work on hard constraints, and in hard constraints like this, you cannot really exploit the constraints, but you need to have a bouncing behavior. In such constraints, you can have the experience and the knowledge from the past behavior, and you can actually extend it to understand how I can move in the next step. Putting all this together and creating a self-tuning impedance behavior, you will see that if you even embed a good trajectory planner with high and low impedance, this will not, the task will fail due to high impedance, because it will basically, when you have a rigid robot, you will have really high interaction forces between the robot and the environment. When you have a very compliant robot, the robot will not be able to overcome the obstacles. For instance, if you have some cluttered spaces. But when you have self-tuning impedance, as I was mentioning to you, you can always tune your impedance values according to the trajectory and according to the constraints that you receive from the environment, only through touch. So this robot has no clue how this maze looks like, but it goes through by feeling the forces and by navigating through and processing the interaction forces, is able to perform the task. Another really nice interaction scenario can be when you're dealing with the mobile robots. This is one of our recent designs that we call it MOCA, which is Mobile Collaborative Robot. The touch here means that basically you can control the robot through the force sensing or torque sensing that you have in the arm, or through the capacitive sensors that we have developed and put through the mobile base. If you're active in robotics community or in basically locomotion of wheeled systems, you know that most of the wheeled systems are blind to touch, because most of them are velocity controlled and they use basically only vision information. However, we integrated this system, and it's really useful not only for interaction, but also when you have uncertainties coming from vision or bad planning, you can actually avoid such collisions and adapt your robot behaviors in a way that you're not creating any bad incidents between the human and the robot. So you might say it's good to plan robot interaction based on visual data. It's good to plan robot interaction with the external environment based on haptic and force data. And of course, it comes very natural to combine them. The first answer is yes, of course. For instance, if you're relying on vision, you're grasping a box, but since the center of mass of the box, due to the placements of the objects in the box it might be different and it might cause a failure, it would be really nice to exploit also haptic data to increase the robustness of grasping. So here my colleague Luigi basically changed the center of mass of the box by just putting a heavy object somewhere in the corner, and the robot, by feeling, of course you cannot see what's happening inside, but by feeling you can actually do the first guess and then feel the system and then basically perform a really reliable pick and place and manipulation task. So this is the first really nice outcome of obviously merging visual and haptic information. But of course, if you want to add some level of smartness to the robot, this addition is not so intuitive, because it would depend on so many
Rush, I cannot hear you anymore. Still don't hear you. Why? I don't know if it's my problem or.
I can't hear him either.
Okay, thank you.
Hello?
Yeah, now is
Okay.
now you're back. Okay.
Super, sorry about that. I think
Yeah.
technology gave up at some point.
Yeah.
All right, you can still see my slide, right?
Yes, we can.
Okay, amazing. So so the plan, the trick is how you can actually combine this data. Of course, this, as I was mentioning, I don't know if you heard about this, it would depend a lot on the level of uncertainty you have from visual sensing and force sensing. It will also depend, if you're considering robotic applications, of if those uncertainties are in your favor or not. Just to give you a very easy example is, imagine you're applying a vision-based grasping algorithm, and you're asking the robot in one shot to look at the object, position the object, and go grasp it. And you have two algorithms to compare. And you have algorithm 1 that comes and picks the object from here, and the algorithm 2 that comes and tries to pick the object from there, and it might fail. So obviously, everybody might say that algorithm 1 works perfectly and works better. But there's a really, really slight chance that all the uncertainties that you have in the system, in the vision errors, the robot calibration errors, and everything is more in favor of the errors of algorithm 1. That is why algorithm 1 works better than algorithm 2. And in fact, if you implement algorithm 2 in a better calibrated vision or robotic system, will perform better. So it's really important to understand what are the sources of the errors or uncertainties coming from the system, that you can calibrate how much confidence you have in using visual data and how much confidence you have in using the force data. Just to give you an example of this, for instance, imagine a very nice and easy for humans task of box filling. This is one of our use cases in the European project that I'm coordinating. It's basically a person is taking these items and filling in these boxes. So if you realize, and also our human studies showed that when you have a really good perception of the environment, when you really see the object and the environment, you can perform really precise movements. You can actually go to the target and put the object there like a very precise robotic pick and place task. But if the person's attention is towards somewhere else, or you have some scattered, let's say, visual information, what you usually do, you exploit touch. So we actually blindfolded some people. When you blindfold people, what they do, they have this sliding strategy. You always start from a really safe area and slide the object towards the target, because you want to exploit, as I was mentioning, the uncertainties that exist in the environment. The constraints that exist, because it basically simplifies your planning. So we replicated this. We combined some sort of visual planner plus impedance, or let's say in a way to self-tuning impedance planner that exploits the constraints. So we have this occupancy grid mapping through the perception system that we have. This is a very flexible box filling, and it permits a person or any disturbances that happen in the environment to be adapted and responded. So here my colleague Pietro is adding more objects, but the robot is always adapting through visual perception. But of course, we added some noise to that, and through this exploitation of the environment, starting from safe guess towards more constraints basis, we were able to basically adapt on the fly and perform this really, really difficult and flexible task. And the final task would be the peg in the hole. We replicated the same strategy in object resorting. So basically, imagine you have boxes in the objects in the box, and you want to resort them. Again, you can define a strategy. This is my desired pose, and balance it between how much confidence you have from the vision uncertainties you have, and how much confidence you have from the force tracking, and then you can actually balance. Again, this will let you to comply with the disturbances that you have from the system. Let me go to the laser pointer, yeah. And here again, the system will re-identify it, and on the fly to change everything and do the replanning of the system. So in this motion, the impedance of the robot is changing all the time to make sure that you have a very really good, nice behavior with respect to the constraints. And what it means that if I have a really good impedance behavior, for those who are familiar with the stiffness control, so if you have a rigid constraint in this direction, if you're rigid in the direction of the insertion, if vision will give you some level of uncertainty, you will arrive here and you will create high interaction forces, and you will break the object or the robot itself. But if you have a good impedance planning, you can actually comply with the environment. And this really nice impedance planning, you see, can help you a lot with the trajectory planning, with the processing of the data that you have from the vision, and permits you to have errors there. And you don't really need very good precise motion planners based on vision, or solely based on kinematics, and it will help you a lot to achieve the task. Another really nice information in balancing visual and haptic information is co-carrying. Imagine you have a rigid object. In robotics, most of the time when you're considering the co-carrying tasks is through admittance control, which means that the forces that you're applying on the robot side are reflected and they create velocities on the robot through whole body controllers. This is one of our robots that basically we hope to put them on industrial applications, and this will be basically purely haptic-based teleoperation. But what happens if you use the same haptic-based teleoperation in a flexible object or a partially deformable object? So until you arrive to a point that you will be able to create those forces like here, when you're pulling, the robot will not feel anything. And that's the point that you might want to balance about the information that you're receiving from the forces and from, let's say, from twist and from the vision to which will be like this, right? So I'm going to look at you and I'm going to follow you until I receive also some forces, and I'm going to process that information to give you the most reliable, let's say, behavior of the robot. This was a good combination. So this can be like basically a teleoperation, right? So you move and the robot moves, and this will be just basically position tracking. But what about partially deformable objects? So what you can do is, as I mentioned, you can take position and force information all defined and reflected in a robot frame of operational frame, and then use that information through some techniques that we have published in various articles to be able to have the right behavior of the system. So the good thing about this is you don't really need to know or model any behavior of the system, or you don't need to really train the system in knowing what the flexible or deformable characteristics of the object is. So it's basically very on-the-fly way of treating interaction or co-carrying of deformable objects. We ran this on several experiments, try to understand on several subjects, try to understand if people find it useful. We did a lot of trajectory tracking and multiple subject analysis to understand if not only the performance but also the usefulness of the approach is good. And apparently everybody was quite happy in comparison to the existing only admittance-based controllers or only vision-based controllers. We recently extended this to a non-graspable, deformable through of course, these carrying wires and multi-robot scenario, which here you can see the robot again, by collecting the information from the forces and visual data, can plan, coordinate the movements between themselves, and without even knowing what is happening and what we are carrying, can help you with co-carrying non-carryable boxes or non-graspable boxes like that. So enough with the interaction with the environment. Now I'm going to tell you a little bit about how these systems can actually adapt to the human factors. We have a little bit of difference between people that are working on human modeling, because most of human, let's say, analysis are done through signal processing of biosignals. So you get EMGs, biosignals like EEGs, or heart rates and stuff like that to get some physical or cognitive factors. So what we do, we just look at people in a way, especially in physical factors. We use dynamic models of humanoid robots. So why we do that? Because of course these systems are rigid body and they're a sort of an abstract representation of the human flexible movements, but they are much better than a lot of, let's say, models that we have been working on, and they can provide a lot of good information. So we start with the definition of whole body, let's say, like dynamics, floating-based dynamics of a human, which is modeled by the humanoid robot, with and without the interaction with the external world. And when we have the equations, the floating-based equations subtracted from each other, we have a really nice closed-loop equation that tells you how interaction forces, the position of the center of pressure, and interaction forces at feet can, ground reaction forces can tell you about how much you're loading the person. We have been working on making the identification of the human parameters really, let's say, one shot and online. So by providing some postures that minimize the number of required postures for the identification of the parameters through Kalman filters, we are able to identify human thermodynamic parameters, and eventually you can use this information, for instance, here to update the overloading joint torques of the human body. Here, my colleague Luca is picking an 8 kilogram object, and you will see here that this object has an effect of loading on the person, and by knowing that, you can know how you can behave in a sense that will help the person. Then we started looking into some machine learning techniques to understand where the point of contact is by applying equilibrium torque theory, and also by analyzing the likelihood of, let's say, the contact between the person and the external world. So now we can actually estimate where the contact is between the human and the environment and update these models. And then we also look into compressive forces. For those are from mechanics or robotics background, these are basically internal forces that do not create any torques, but these are just joints pushing against each other. It's in fact, in some postures, forces and torques are insignificant, but torques are very significant, and vice versa. So they both need to be considered. As I was mentioning, we considered initially a rigid body model of the human, and you might say, I can agree with you that the hand and legs can be rigid, can be modeled by rigid links, but spinal cord usually is very, let's say, flexible. So how can you make such a huge assumption that it is actually valid? We try to, again, use a robotics approach to model this as a flexible link, but a single link, and through this flexible link modeling, we will able to also tell about compressive loads and forces. In terms of cognitive factors, again, we are looking at people using machine learning techniques. First of all, we can detect where the attention of the person is. So imagine you're doing an assembly task and you have a monitor here that tells you about the instruction manual. You're looking at that monitor, but you can actually know by looking at a person's face where the attention of the person is, and you can define an attention index. By looking at people, also you can tell if people are sleepy or yawning, or they have some attention loss, and this is really important also to ensure their safety when they are working with the robots. In terms of cognitive load, you can capture a lot of information, for instance, face touching, self-touching, or hyperactivities, that there are some really rapid movements that the people have. There are also some indications of cognitive index. So if you put them all together, you can tell how much the mental effort and the stress level of the person is, and eventually create some index saying that, okay, in this particular moment, the estimation is that the mental effort of this person is this much, and the stress level is this much. And I will tell you how we use this information in human-robot interaction. So when you have those parameters, for instance, the physical parameters, what you can do is to use robots to contribute to their minimization. Imagine you're holding an object with a robot, and the robot through your physical model realizes that you have a high torque in the shoulder, and the robot, according to some task constraints, can change the task coordinates and maximize and minimize those torques, right? So for instance, here in this video, you will see that in a let's say handover task, the robot wants to do the handover task in the most ergonomic configuration, which in a sense minimizes the loading effect. But since we are dealing with a multi-constraint, multi-objective optimization, you can actually add more objectives like maximizing or optimizing the force production by this person, for instance. When my colleague is holding a drill, through the vision system, we can recognize the person wants to drill and also put the force manipulability in the optimization process. Another really nice factor will be also to include the future intentions of the person in the multi-objective optimization. For instance, if you're doing a collaboration with the robot and you have an idea of where the person will go in task 2, you can use redundant degrees of freedom of the robot to be able to push, to make the robot basically enable the person to have the minimum path to be able to arrive to the second point. How we can use this in basically cognitive, let's say, with cognitive human factors. Imagine you detect a certain level of stress, and you have a control, let's say, problem that you can, through some robot behaviors, you can reduce stress and you can increase, let's say, not the stress, but also the engagement of the person. You can actually put it in a Pareto front optimization, saying that if very simple would be like if the robot moves fast with a high jerk, so it means that the task will be done much smoother, much faster, and it's good for productivity. But this might create a little bit of lagging behind and eventually stress for the person. So you can put them in a Pareto front optimization and play with it until you personalize for that subject, which is basically like this. You start co-filling the box with a person, and the robot realizes through our algorithms that the person is in rest, which is quite boring, and it starts pushing on this Pareto front optimization to increase the velocity of the execution. If you increase too much, then eventually what happens is that you detect some level of stress, and this stress will be detected, and the robot says, maybe I pushed too much, and then it actually gets back to the point, the sweet point basically, which will be your calibration for that moment that basically implements a trade-off between physical and cognitive factors. And we believe that these models can calibrate and personalize interactions between humans and machines. So in the last part of my talk, I want to also say a few words about the inclusion of a creation of a framework that includes brings learning and optimization together for mobile manipulators. We know that we are all in the era of learning, and learning is really a good hype. We know all its good potential in natural language processing. We know its amazing potential in vision, but still in control, or maybe in some processing, the robustness that we expect is not basically yet in place. So you really cannot rely on observations and few trainings based on a small amount of data and stay close to a robot which is carrying a really sharp object that can basically, something can go wrong and can hurt the person in an industrial environment. That could not be really nice. So usually in mobile robots, especially, what we have is you have a really high level planning problem and you have a control problem, right? So it's been hundreds of years we are working on control. We have really good, reliable and robust controllers that ensure passivity, ensure safety. But we sometimes, most of the time, we don't know how to plan high level, how locomotion and manipulation should look like. So we have been looking into this. We have put learning in charge of creating high level plans in terms of motion and impedance, but we have passivity-based impedance controllers in low level and optimization controllers to make sure that those are tracked in real time. Just to give you an idea of a really nice, basically, representation task, before going that, I will tell you basically all this come to a whole body controller that I was mentioning that controls the manipulation and locomotion aspects at the same time. So imagine a polishing task that basically you want to teach to a robot, right? So it's easy to control a robot and tell a robot to apply a certain force, but definitely it's not easy to tell a robot how the trajectories will look like. You definitely need a professional robotics or similar, let's say, degree to tell you how these trajectories can be generated. But learning can help a lot there, right? So what we did, we kind of looked into problem of learning trajectories and forces through impedance. So we created this admittance-based interface that the person can apply forces and the robot moves according to the forces that are applied. And we learn forces, but in the end, what is really nice is we replicate those desired movements and forces through an optimization, which is basically this one. So this is the external forces that robot can detect when it interacts with the environment. This is the desired force that we have learned from the human, but we can achieve this desired force through an impedance controller. So we can actually change the gain, the impedance gains, have a really stable and passive behavior, and achieve those really nice, let's say, interactive behaviors. Just to maybe give you a very brief example. So imagine here, my colleague John is starting with the admittance interface from start point to the goal point, takes the interface and demonstrates the path. And what we do, we take this demonstrated path and use Gaussian mixture models and regression techniques to detect and encode basically the trajectories and the forces. So what's nice about this interface is that we have developed some priority control that gives you a prioritized motion between arm and the base, and this enables you to have a larger demonstration in a larger, let's say, workspace. So you can see that here, as it was obvious, sorry, by clicking, by pressing one button, the priority of the controller was set to the base, and here Alberto was easily changing the movements of the robot. By pressing to it, was making the robot do the locomotion instead of navigation, and it was really nice. So when you learn these behaviors and put in the framework that I was mentioning to you, obviously, initially, first we wanted to see if the algorithm can cope with constant stiffness values. So basically, you learn the desired behaviors, but you do not change the stiffness. Of course, the robot will start replicating, especially in low stiffness, the behavior. But the bad thing about low stiffness is, as you know, you cannot really regulate, arrive to a good level of force because the robot is very compliant, and the peak forces are much less than the desired. You can also try to create a really stiff robot, but the stiff robot, basically, if your basically demonstrations are not exactly as your task execution, it will create really jumpy and jerky movements, which are not good for control and not good for the performance of the task, basically. So if we put now the method that I explained to you through the optimization of the impedance to arrive to the desired force, it is really nice that you can see the behavior is really, really smooth. The desired force is being tracked through the optimization of the stiffness, and the desired trajectories are perfectly matched. But what happens if we have disturbances from the external world? Again, if you only have low stiffness, what happens is that obviously the reaction of the robot to the disturbance is good because you're very compliant, but then again you have force tracking. Your detachment from it results in detachment of the robot from the surface, which is bad for polishing and for the tasks that are contactful. If you make it really stiff and constant stiff, again, disturbances will definitely be rejected by high forces, and the robot will basically go into a security state because the high forces are being detected. Now, if we put our controller, so also you will see here that the high stiffness is the person is basically interfering with the robot, and the robot is really stiff and always tries to objectify the external disturbance. But here, if you have the controller that I was mentioning that we implemented, you can always keep the contact. You can always track the desired forces the way you want. The trajectories are being achieved, and then you can see that the robot behavior response with respect to really, really harsh external disturbances is really robust and reliable. Here again, in different directions and different disturbances are dealt with with a very, let's say, desirable behavior. So this concludes my talk. Just trying to give you a few key messages that I was hoping to tell. I'm from robotics background, so my messages will be very much in line with the robotics implementation. So for those who are active in motion planning, I think it's really important, especially in robotics, that we have we include also methods or maybe control techniques that facilitate our motion planning problem. And obviously, us humans use a lot our touch and our impedance, basically regulation to perform contact-rich manipulation tasks that require motion planning. And this can also facilitate robot controller, and it will permit some level of uncertainty for the kinematic planning, and will let you to perform with high level of let's say robustness and reliability. If you're using vision, it's really important not to trust a single shot. It's important basically to receive feedback. So if imagine you want to locate an object in space and we locate it, and then with the robot or with the mobile system, we want to arrive to that point. It's important that we do it continuously, so we make sure that all the other uncertainties in the system, the calibration, the robot movement planner, or anything are informed about the basically the visual uncertainties that we have. And it's quite important to not to trust on single shot vision. As I was mentioning, it's quite important to balance visuo-haptic information to get the best of each, relying on this uncertainty levels that we have from either one of them, and how much confidence we have from the sensors and the data that we receive from each one. On the human factors, it's what I was mentioning is we are looking into postures and movements, but these postures and movements contain a lot of dynamic information. For instance, if some of you are trying to push a heavy object, by looking at your posture, I can understand if the object is heavy or light. Or when you're accelerating an object, I can tell you pretty much how much is the mass, like it's a light, or if it's a heavy object, only by looking at your acceleration profile. Human posture contains a lot of information that I was mentioning, and especially for robotics, I always say that it's important to validate every control and machine learning in contact. It's we would like to. It's good to do planning in free space, but things can really go nasty when you're in contact with the environment, and it's important to test everything when you come to a contact. Again, I would like to thank your attention and acknowledge funding of my research and the great work by my team. Thank you very much. If you have any questions, I'll be happy to answer.
Thank you, Arash. Thank you. Very interesting talk. So, is there any question from the audience? As I told you at the beginning, you can feel free to open your microphone and put directly question to Arash, or if you prefer, you can also write to the chat. I will monitor the chat as well.
Yes, I would thank you, Dr. Ajoudani, for your interesting presentation. And I would know which is the time latency in the human-robot interaction when you record different features, like, for example, heartbeat rate respected to the robot reaction, as you showed in the presentation.
Right. So in only one of the works we used heart rate variability, and it was about 100 hertz, if I'm not mistaken. But most of the time we are relying on body posture estimation, body posture tracking, which we are using basically libraries like OpenPose, AlphaPose, and we've recently implemented our own 3D multi-camera tracking. And there we arrive up to 30 hertz. So it depends. Of course, in the body, human movements, even hyperactivity, usually within 10 hertz, you can understand if the person is going through some, you can detect hyperactivity. And in most of the cases, if the person is doing face touching and stuff like that, you really you can, up to 10 hertz will be definitely enough. But our robot controllers are real time. So basically, as fast, everything basically, even if the human tracking can be up to 50 or 100 hertz, in a sense that if you can adapt and update the human states within 100 hertz, but the robot controllers are usually running at the high level, usually in 1 kilohertz, but at the low level, it's even more. So you make sure that the implementation of the control is really reliable and robust.
Thank you so much. Yes, thank you so much, because the real time is very difficult to reach.
Of course, with humans especially, it would be really difficult to arrive to that point. But again, it depends on the type of data. Of course, dealing with the EMGs or other kind of signals, human signals, biosignals, you definitely need to go beyond kilohertz. It also depends a lot on the movement. But so my point was, a lot of information, high level, let's say high frequency information, can be captured in low frequency movements. Not everything, obviously, but sometimes. So for instance, one really easy example will be if I'm sitting in this room and I'm sweating. So easiest will be to go measure the temperature with a sensor of temperature, even if it's really slow. But a hard, let's say, way will be to monitor my rate of sweating and then create a model that tells me what this rate of sweating means in terms of temperature. So it's always good to find the final element or the easiest element that will tell me about the parameter that I'm trying to monitor.
Thank you.
Yes, thanks for your question.
Thank you. Other questions?
I have one
Please.
question.
Please.
if
Yes,
possible.
please.
I have two questions, literally. The first thing is when you try to pick the things, like you only focus on the force of the robot, or you have to also assess the load of the objects that you are going to pick. So how you manage that thing. And when you polish, if there is someone on the desk putting its hand, how it affects the robot. On this question, when it learns this polishing task or any task, are you using a kind of machine learning algorithms like reinforcement learning or active inference? If so, how do you do the action part? How do you learn the action part? Thank you.
Very nice question. If I understood correctly, the first question was about how do we infer the weight of the object when we are picking the object. So basically, if our robots are all equipped with 6-axis 4-stroke sensors. When you're grasping an object and you immediately know what's the weight of the object. And if you're moving it around a bit, you can immediately model the inertial behavior of the object, right? So basically, you can immediately, after a few small movements, you can have a really precise model of the mass and inertial parameters of the object, right? So it can be very easy to get that information. So the robot can learn and estimate really fast what the mass of the object is and adapt. So that's one. The second question, the learning we are using here is that particular video that I showed is not reinforcement learning. It is we use GMMs and GMRs. So basically similar to dynamic movement primitives. Reinforcement learning is also, we've been recently looking a lot into implementing this one, but of course the input space is in this case is the trajectories and forces of the human demonstration, the trajectories that are demonstrated through admittance interface and the forces that are applying by the robot. So what you were mentioning is if there's an obstacle, if for instance a human hand is on the table, this will be another high-level strategy. So through the impedance planner, you will definitely, since it's compliant, you will be compliant and you will definitely be safe in a sense that you want to interact with the person. But this would be the low-level safety. So the high-level safety would be definitely to perceive the environment and to replan for the trajectories. And that's not included in this work, but it might, an easy extension will be to track humans in real time through the techniques that I was showing you through the cameras. And always you see, anytime you see there's a collision or possible collision between human and the robot, to identify it and replan the trajectories of the robot. There are several groups that are working on this. Basically, this is called human safety and human-robot interaction. And there are many, many methods you can do by changing robot trajectories, by making the robot stop, or by basically making the robot very, very compliant. And these are the strategies that you can implement. And they can be implemented through control, machine learning, reinforcement learning, or anything else.
Thank you.
Thank you. Thank you.
Yeah, my pleasure.
Well, I have a couple of questions myself. So the first one seems to me that something that you showed, especially in the last part of the presentation, is related to imitation learning in some sense, because you are trying to redo the actions that a human is doing. So did you investigated, or do you know anybody, any research group doing this kind of imitation transfer learning from robot to robot? So a robot that is observing another robot performing an action and trying to replicate, maybe also if the robot are not identical, but they have some difference each other. So do you know any, or do you ever do any research on these aspects?
So we did a few years back. I'm trying to find something to show you immediately. We did some research in that direction. It was really interesting for us to understand if robots can learn from robots. Obviously, the first question, yes. Let me share again this quickly. So a few years back, we started looking into how robots learn from humans, as you were mentioning the imitation. You can see my screen, right?
Not yet.
No, sorry.
No, yes. Oh, yes.
How robots can learn from humans, and then basically we said, okay, let's consider a contact-rich task like this, where the person is basically, is showing basically here. The person was showing the robot to how to saw, and the robot here was learn. And then we said, okay, can we make a robot to learn from another robot? So here again, we looked into this robot. You can see jumps up and down. Is a novice robot. This is a skilled robot. But then after 30 seconds, they start optimizing the parameter. So here it would look stupid because the robots are really much the same. So you can say you take this code and replicate it there. But what matters here is, first of all, everything is learned in the task space, and the controller takes care of the rest. So if you learn everything in the task space, even if this is a 20 degree of freedom or a humanoid robot or anything else, it can be implemented, and the controller will take care of that. So it's everything is a trajectory space. And the second important thing for us was to make sure that the synchronization of the movements are basically happening. So just to conclude, what I think robots learning from robots is not a thing yet, because people think that its replication is very easy. You just take the code and put it there, and mostly the learning is done in the operational space, and the controllers basically should be very customized and very personalized for each robot. But I was really interested. I'm still interested in this a lot.
Yeah, I was noticing, for example, in your presentation, in the slide, I think towards the end, the slide 48, where you show the last part. Well, when the human was performing the action, basically the robot was still, while when the robot was redoing the action, it was moving the wheels. So I was asking why this different behavior of the robot in some sense.
Very nice point. Yes, very nice point. So the thing is that like us humans, arms and legs are basically can be controlled separately. You can use the arms, you can use the legs. Most of the time when you're very close to a table, for instance, you're only using your hand to arrive to an object. But when you're far, you're using your legs, and somewhere in between you're coordinating the ones in two. And the criteria that you usually coordinate between arms and bases it depends on the amount of energy you're consuming, it depends on the distance, it depends on so many things. In that particular work, the only thing we considered was the distance. So to make sure that if you're so in close distances, the arm was having the most of the mobility, and when you were basically anticipating to go towards larger distances, you were losing the base. So what we basically did, again, we learned everything in the task space, and from task space, when you project everything in the robot joint space, you can regulate and get that weight, how much the arm, how much the base, and you can tell if the distance is low, give the high priority to the arm. If the distance is high, give the high priority to the base. And somewhere in between, use both. And this was the behavior we observed, and it was quite natural, and we liked it.
Yeah. So you can also say, for example, I don't want to use the wheels, say the legs, because I don't know, they are consuming too much energy, and then you can.
In this work, no, but we are looking into this now, basically.
Yeah.
So there are too many factors you can include. I think us humans, most of the time, there's a debate, but there's a lot of studies that they say we are mostly looking into energy to save energy. But I highly doubt so, because walking is a very energy efficient thing. So basically, I don't know how we regulate our body, whole body movements, the redundant manifold or whatever. This time we only looked at the distance, and
Okay. Yeah, I have another curiosity on the first part, when you show us the co-carrying the robot. Helping people carrying ungraspable or too
Yes.
heavy. And you, if I remember well, you also say that the robot is using visual clues, not only the forces. So, but in that specific case, seems to me that, for example, the human was completely hidden from the view of the robot. So actually, the visual cues are from cameras that are mounted on the robot
in that
itself.
particular good observation. In that particular case, we used a suit, an inertial measurement suit.
Okay.
And so basically no obstacles could avoid seeing the person.
Sure.
And of course in the it would be problematic when you use vision system, and the vision system, for instance, if you have basically obstacles like that will be possible. But if you put yourself in that scenario, will be pretty much the same. So if you basically close your eyes and somebody holds a rope on the other hand, you will not be, it will tell you that I'm holding this rope, you're holding the other hand, close your eyes and try to follow me. It will be impossible. So we really need to have a good vision. Even a scattered vision would be good. So nowadays with the visual tracking systems getting better and better, you have a good estimation, especially with the obstacles, because they take the history and they do some estimation on time on top of that to understand where you are. Again, how much confidence you will have there, it depends. If you lose tracking of the person, then it's good to put your confidence on the force sensing and saying that I don't know where the person is, I don't want to do something crazy, hurt the person or move some movement. So let me see when the forces will come to react until I have a good behavior, vision and tracking from the person.
Are you using also, for example, some fixed cameras, some environmental, like
We are
CCTV?
working a lot on that now. So we are working on so of course there are Vicon, multi-track systems and stuff like that, but we are working on, we have created, and now we are actually submitting the paper now, on multi-camera based visual tracking of people. So basically you have an industrial environment, you have multi-cameras installed, you can actually track the person very easily, and this will make it more robust to occlusions and movements and stuff like that.
Sure. Thank you.
Yes.
So any other question from the audience? Okay, so if not, I think we can thank the Arash Ajoudani once more. So many thanks for accepting the invitation, and also thank to all of you who attended the meeting.
Thank you very much. It was a pleasure. Thank you.
Thank you.
Bye, everybody.
Thank you, everyone. Bye-bye.
Bye.
Bye. Thanks.
Thank you. Bye.